Hey YouTube, Booth Dog again. Here we are, Tuesday of our second week of this new experience for us all. Hope you're doing well. Continue to reach out to me if you need absolutely anything. Before we get started for today, just want to point out that today's video is sponsored by pencils. Lots of pencils. And not those trash mechanical pencils either, but real wooden pencils that actually work. Now, since some of you have started complaining about the lack of, shall we say, decent editing in some of these videos, I guess I'll capitulate. Let's bring on Mr. Boothman and get started. All right, let's go. All right, good morning, happy Tuesday. Let's jump back into 8.3. Again, we're going to spend the rest of this week on 8.3, and then we'll start to review our unit next Monday and Tuesday. Today's exit ticket will ask you to submit pictures of the third page of your 8.3 mastery sheet. I want to see that you've worked through and completed all of those problems. This will be put in as a completion grade. It's our problem of the day. The only difference is you're going to take pictures of your work and then upload them through today's Google form. So if you're having any issues with uploading, please let me know. If you don't have, just take pictures with your phone, but if for some reason you don't have access to that, just reach out to me, let me know. I'm more than happy to work with you. This will be due by midnight tonight. Okay. Now, we have been discussing the washer method for finding volume of solids of revolution. We talked about revolving about the x-axis and the y-axis. Today we're going to talk about revolving about any other horizontal or vertical line. Don't worry, we're not really going to get into actual diagonal lines here, revolving around those. It does get a little trickier if we try to take that into account, but horizontal and vertical lines, not too much more difficult than what we've done so far. So I'd like to do some examples and then talk about a general formula for any time we're using washer method. So this is still 8.3 continued. All right. What if our axis of revolution is not x or y axis? Let's consider, here's an example. Let's consider the region enclosed by y equals the square root of x plus 2 and y equals e to the x. So we're actually going to break this apart into a bunch of different pieces. So part A, rotate about y equals -2. Let's start by drawing a picture of this. Now, these are graphs you should be able to sketch on your own without the use of a calculator. Y equals e to the x. We know that passes through the point 0, 1. The square root of x plus 2, well, we know the square root of x is the top half of a sideways parabola. We're adding 2 on the inside. That is a horizontal shift to the left. It's the opposite, so to the left 2. So it ends up looking something like this. Okay, so we're talking about this region right here. And I'm going to erase the rest of our graph. We are rotating this about the line y equals -2. So take this shape, and it's coming up out of the board, rotating around this line. And that's where it goes back into the board once it's on the other side of this line. Okay. So is it as simple as just saying we are going to do our small radius is the closer function and our bigger radius is the taller function? It's not, because that function value is giving us the distance from the curve to the x-axis. In this case, we rotated around the line y equals -2. So we need all of this distance, and we need all of this distance. All right, the good news is there are a few similarities to what we did before. Okay, the first and foremost being that our formula is the same thing. Okay, we have the integral from a to b of pi big R squared minus little r squared dx. Because if we imagine taking a cross section here, okay, so slicing this out, it is just a much bigger washer. Okay, so this part right here is our filled in circle all the way around the washer. And then this big gap in the middle is the inside of the washer that we need to subtract away. Okay, so this is our small radius, this is our big radius. Now, we need to think carefully about what this big R and little r are going to equal. Okay, so let's start with little r. We know that this distance right here is just the function value. Now, what is that function value? That lower function is e to the x. But that's not the entire radius. We also have this distance right here, which is 2. Okay. So what is little r? It's 2 plus that function value at any given x. And big R, well, we have this 2 here still, and then we want this distance now, which is the top function, square root of x plus 2. Okay, so take a second, pause, process what we just said. This 2 is consistent at any point along our shape, and then we have to add that to our function values. We need our limits of integration. How do we find limits of integration? Well, we need to know where these two functions intersect. So we're going to find our points of intersection. How do we find points of intersection? Well, if you had your TI-89, you'd use the solve function. Otherwise, set them equal to each other, solve for x. Also, you can use Wolfram Alpha, as I keep mentioning. I'll go ahead and post a link to that with today's video as well. Okay, but regardless of how you get these limits of integration, we get negative 1.981 all the way to 0.448. Okay, so this is negative 1.981 and this is 0.448. So I guess my graph isn't particularly accurate, but that's okay. Times pi, or I'm sorry, integral of pi times big R is 2 plus the square root of x plus 2 squared minus little r is 2 plus e to the x squared dx. Feel free to do this by hand or use calculator, use Wolfram Alpha, and you should get an answer of 19.724 or 19.725, depending on whether you are rounding or truncating to 3 decimal places. Okay, so same basic ideas that we had before, that we've looked at for a few days now. The only difference is now that we're rotating about a different axis of revolution, we need to take into account that added distance in our radii. Okay. Just one last thing to think about, I know. So pause this if you need to finish writing this down. Otherwise, I'm erasing. And let's look at part B. Part B is the same shape, okay, but now we're rotating about the line y equals positive 2. So we had our graph. And now we're rotating about the line y equals positive 2. So take this shape, comes up out of the board, rotates around this line. Here's where it's going back into the board. Our volume is going to be the integral from, well, we have those points of intersection, thankfully. We don't have to do that again. Pi times, we need big R and we need little r. All right, so what is, if we take a cross section, still a washer, we still have little r, we still have big R. Okay, but now this distance right here is little r, this distance right here is big R. So starting with big R, well, what is this entire distance here? We know that this is the line y equals 2. So that whole distance is 2, but we only want this piece right here, which means we need to subtract this distance here. And what is that distance? Well, that was our e to the x, the function value there. And what's little r? Well, the whole distance is 2, and we need to subtract away this distance, which was this function value. So, I know it's a little tricky. Now, the way I like to think about it, and this works for every single problem, is that your big R is always the function, or it involves the function furthest away from your axis of revolution. And if we see, if you imagine you're standing right here on this axis, which function is furthest away? Well, that's e to the x. And little r is always involving the function that's closest to the axis of revolution. And this general rule of thumb will work no matter which axis, what line we're rotating about. Just imagine you're on the axis of revolution, okay? Big R, that's going to involve the function that's furthest away. Okay? Here's our integral. Evaluating that integral with a calculator, 8.535 or 8.536, rounding or truncating. Okay. So take a second. Moving on to part C, we have a couple more examples today. I know today's video might be a little longer than usual, I do apologize. Same shape. Now we're rotating about the line. Not y anymore. X equals -3. Here's our shape. Okay. We're rotating about the line. X equals -3. So we are taking this shape and it is rotating around this line. That's where it goes back into the board. Here's our shape. Now, if we try to do a vertical cross-section like we've done, it gets very, very, very difficult. Especially, I mean, what does it mean once we're in here? There's no actual shape in there. Okay. This problem is much easier if we integrate with respect to y. So just like when we were rotating around the y-axis, we integrated with respect to y. Whenever we rotate about a vertical line, we're going to integrate with respect to y as well. So imagine taking a horizontal cross-section. So slicing into this, cutting that out. It's another washer. Whole reason we're doing this. This part right here is this filled in area all the way around, and then in here is our big gap. Same process, but now we're doing everything with respect to y, which means we need limits of integration that are y values. We don't want from here to here anymore in x values. We want from this y value up to this y value. How do we find that? Okay, well, we take our two functions and we solve them in terms of y. So x equals y squared minus 2. Y equals e to the x. Solving that for x, we get x equals the natural log of y. Now we can use any solving function in a calculator or online that we find to solve for our particular y values, just like before, and we should get 0.1379 and 1.564. These are the y values from here up to here. Pi, and then we need big R, so this, and that rule of thumb still applies. If we're standing on this axis, okay, which function is furthest away? Remember, this is all in terms of y, so that is actually the natural log of y. Okay. And if we're talking about y values, then we're thinking about this distance, which is the natural log of y, and we need to add that to this distance, which is 3. This is the line x equals -3. And I promise we will have a nice general formula in just a second, but right now we do have to, I want you to think through how we're getting these radii. Little r, it's the closer function. So we have that distance, which is y squared minus 2, plus that distance, which is 3. With respect to y. Plug all of this into a calculator, and we get 15.539, or 15.540, rounding or truncating. Okay, kind of tricky, I know. I want to do one more example and then we'll generalize this to a nice formula. Part D, we're rotating about the line x equals 1. So taking this up out of the board, rotating around. Again, it's a vertical line, so we should integrate with respect to y. That means we need our y values for our limits of integration. Luckily, we solved for those in the last problem. We need big R. That function would be furthest away. Now, what is this entire distance? 1. But I only want this distance, which means I need to subtract away that distance right there, which is just that function value. In this case, the square root of x plus 2 in terms of y is y squared plus 2. So our big R and our little r works similarly. Okay, the whole thing is 1. We need to subtract away this distance, which is the natural log of y. And we get 12.720 or 12.72. Okay, let's generalize a little. Now notice that sometimes I'm subtracting in here, sometimes we're adding, and that totally depends on where our axis of revolution is. We're trying to find those distances. So sometimes that means subtracting, sometimes that does mean adding that number. However, since we're always squaring that value, in fact, anytime we want to find a radius, a formula that will always work without you having to think about those distances is simply here's what I mean. For that last problem we had, big R is 1 minus parentheses y squared minus 2. If I'm squaring that, that ends up being the same value as y squared minus 2 minus 1 squared. Putting the function first, subtracting the axis. Our first example today, we had 2 plus e to the x for little r. If I'm squaring it, that's the same value as e to the x minus 2 quantity squared. This works every time. The only difference is that big R, we're using the function that's furthest away from the axis. Little r is the function that's closest to the axis, and that goes first. So this general rule of thumb, this formula, works every time. You should now be able to complete numbers 21 and 22 on your mastery sheet on that third page. Again, your homework is to complete that third page of problems, take pictures of it, and upload those through the Google form by midnight tonight. I will be putting that in as a completion grade. Please practice. We will spend the rest of this week practicing these problems. That's it for notes for this section. Thankfully, because I know today's video is a little long. And we'll practice and then start to review our unit. So join our Google Meet if you have any questions. Reach out to me if you need anything. All right, well, I hope that was informative for you. Continue to reach out to me with any of your questions or concerns. Yes, Shelby, it's okay if you have questions, just reach out to me. You too, Arter. And I'll see you tomorrow.